5 was about magnetic molasses. So, the phenomenon of magnetic molasses refers to the significant slowing of charged particles, such as ions or electrons, through the combined effects of magnetic fields and electric fields. By applying a magnetic field to an experimental setups, particles experience a Lorentz force, causing them to spiral and lose kinetic energy as they interact with their surroundings. The objective of this lab was to understand how magnetic fields can be used to control particle motion, observe the resulting behavior, and quantify the energy dissipation through experimental measurements. So, the purpose of this lab was to observe the data from a magnet falling through a tube of conductive aluminum foil and then compare these results to a computational model. And the average time for the magnet to fall through our tube experimentally was 1.504 seconds. So, some fundamental principles employed in this lab. So, obviously, the formula for magnetic fields or a magnetic flux, which says that E dot dl, the integral of E dot dl, is equal to negative d phi dt. And then the formula for magnetic flux, which says that phi b equals the integral of B dot dA, or just times A. The magnetic force, which in this case, because it's a circular ring, we would use the formula for the circumference of a circle, which is I times 2 pi r b sine theta, because it's the cross product. And then Lenz's law, which says that the electromotive force is equal to the voltage, which is equal to negative of the magnetic flux, the change in magnetic flux, d phi dt. So our system for this lab was the falling magnet, as can be shown here. The surroundings were the aluminum foil tube and the earth, which generate a magnetic field. And then the forces on the magnet were the force from the loop, the magnetic force from the loop, and the force of gravity from the earth. So the procedure here, first we marked to the north pole of the magnet, then we measured the mass of the magnet, we measured the width, inner radius, and length of the aluminum tube, and then we dropped the magnet through the aluminum foil 5 times, and for each time we measured how long it took the magnet to leave the aluminum tube. So this is the computational model we used to be able to predict how long it would take. And this took in many parameters, including the mass, the magnetic dipole moment, the ring radius, width, and a lot of other forces. And then through this, it was able to calculate the forces and be able to predict how long it would take for the magnet to fall through the magnetic loop. So our experimental results for all 5 attempts can be seen here. It's roughly around between 1 to 2 seconds for each trial. And then some possible sources of error that could have resulted in differences between the computational and the experimental results were errors in finding the magnetic north, improper timing of entry and exit of the magnet, or the magnet contacting the tube as it fell. What if the resistivity of the conductor were reduced as close as possible to zero? How would the dynamics of the falling magnet change? So because of Ohm's law, the induced current would be very large if the resistivity was decreased, which would therefore decrease the velocity of the magnet as it fell through the tube, and that would increase the time it would take to fall through the tube. And what if holes or slots were cut into the tube? How would this affect the ring currents? So the model would take fewer rings that it has now if holes were cut in, which would there decrease the induced current and therefore the magnetic field, which would cause the tube to fall through faster. Thank you.